What is that thing? Well, I'll tell you what that thing is. It's a drawing. Obviously, it's a drawing of a marble on top of a hill. It's sort of a cut. It's like a side view of like a wood cutout with a little groove in it. We're going to take a marble. We're going to let it roll down the hill and up the hill and so forth and do what it wants to do, rolling up and down this hill here. What I'm going to introduce you to this video is a way of visualizing total energy, kinetic energy, and potential energy. We've talked about the buckets, right? About like when the bowling ball falls off the shelf. At the top, all of its energy is stored up in the potential energy bucket. As it falls, it loses energy. It doesn't lose energy. It doesn't lose energy at all. It loses potential energy, but at the same rate, it gains kinetic energy. So the total energy of the bowling ball remains constant. Okay, this idea of buckets. Okay, we're going to take that idea and visualize it a different way. Here we have a ball on top of this hill. Okay, we're going to just give it the slightest little tap. It's going to roll down, roll up, roll in, and come back, do whatever it's going to do. And we're assuming that this is that there's there's no losses to friction here. Okay, which is pretty close to true. If we oiled it up and made it nice and smooth, there would be very few losses due to friction. Now what I want to do here is, you notice I've labeled my axes X and Y. Okay, I would like to change the label of my Y-axis. We're still going to have the same thing sitting here. It says object, this wood cutout or whatever this thing is with little hills on it. But we're going to think of the Y-axis not so much in terms of height, although it is that obviously, but in terms of energy. So it's a one-step sort of abstracted, but stay with me here. Stay with me. I think this is going to make some sense to you. The ball starts off here. It starts off at rest. So if it starts off at rest, all of its, right, the total energy, we'll put this over here because it's so important, is K plus U, kinetic plus potential. If there's no kinetic energy at first, we release it from rest, then all of the energy, the total energy, is potential. In other words, this mark here, vertically across, represents not only the initial potential energy, but the total energy, because at the beginning, all of the energy is potential. So this is E equals K plus U. Now at the top, all the energy, like I've said now 3 times, is potential. Okay, but I want you to see what happens. As the ball goes down the hill, what happens to it? It speeds up, gaining kinetic energy. Also, as it speeds up, it goes down, losing potential energy. So let's take a snapshot of the ball at the bottom of the hill here. It's fallen a long way. Now it's in motion, right? It's come down, it's moving up. But at this instant, at this snapshot, it has lost almost all of its potential energy and is moving very fast. So what we can do is we can represent this distance here as the potential energy. And let me see, a good color here will be blue. This distance here above it as its kinetic energy. So at the bottom of the hill, that's a nice sound, isn't it? It's got a whole lot of K. This pen. It's killing me, folks. I'm going to need to pick a different color here. At the bottom of the hill, it's got a whole lot of K, but very little U. Okay, orange for that. Let's try for yellow. Here we go. So we're going to have K here. Yeah, that's better. So at the bottom of the hill, it's got a little bit of U, and a whole lot of K, but they still add up. This little bit plus that much adds up still to E. Okay? So K plus U is still E. We just have a whole lot of K here and very little U. So the ball is going to be going really fast down here. In fact, the fastest that it goes on the whole roller coaster here. It's going as fast as it ever will go. That's because the gap between the track and the dotted line is the largest. So this big gap there means it's really moving fast. When it gets to the top of the next hill, you've ridden a roller coaster, you know what happens, it slows down. Up here, this, again, this gap here represents U, so it has gained potential energy and lost kinetic energy. Now it has less K than it did before, but it's still moving. And that U plus that K still equals the total energy. I'm going to change the way this looks here. This is a little confusing. I tried to do it because of space problem here, but this little gap here is U. I think that line was a little confusing to me anyway. That little bit down there is U. Okay. That arrow I'm sure is too small to see, but let's check. Yeah, that's fine. That little bit of gap there is U. So the bottom is, the below is U. So basically the elevation and the potential energy are the same, which makes sense, right? Because the potential energy is mgy. So as y goes up, U goes up. As y goes down, U goes down. That's what I'm showing you here. When U goes down, when y goes down and it gets to a low point, U is very small because y is very small. When it rises, it gains potential energy. Y goes up, U goes up. In this case, it's gained a lot of potential energy, but it's still moving at a pretty nice clip. It still has plenty of kinetic energy. In fact, there, it's pretty close to having half of the energy in the potential energy bucket and half the energy in the kinetic energy bucket. Maybe a little more than half in the potential, but the water is the energy is pretty well split between the two buckets there. Whereas here, almost all of our energy is in the kinetic energy bucket and very little of it is in the potential energy bucket. When we started off, it was all in the potential energy bucket. And you see what's going on here. When it's here, it's rising, but it's got more potential energy than before, than the previous spot. And it's got less kinetic energy than it had, and it actually has about the same. The way I've drawn it here, it has about the same. So it went down, came back up to about the same height. So really, its split here is about the same as it was the previous time. Okay? Now, as it rises, it loses potential energy. As it rises, it loses kinetic energy, gains potential energy. It will never get higher than this point right here. When again, all of its energy has been converted to potential energy and it is momentarily at rest and has no kinetic energy. So at these two places, all the energy equals U there, and energy equals U here. Okay. It equals U plus K really, but K is equal to 0. So these 2 points here are known as turning points. Where all the energy is potential and none of it is kinetic. So then you can figure that at any point, like at this point here, the ball has a lot of potential and a little bit of kinetic, right? It's moving but not that fast. As it goes down, it gains kinetic, loses potential, and then as it rises, it gains potential, loses kinetic, and so forth and so on until it rises back to its original height where it has all potential again, and it would just end up going back and forth ad infinitum, back and forth, back and forth, back and forth. It's just a way of visualizing things. It's called a potential energy curve, and they exist in other contexts as well, but that's your first one. We'll see more later this semester and also next semester. So there's a potential energy curve. It's just a way of visualizing the exchange of potential and kinetic energy as the system evolves. There you go. It's handy. And once you sort of have it in your head, it's a really good guide.